done with Alejandro Infante and Juan Pablo Sandoval. So we are coming from Chile, and we're going to talk about expandable collections in Pharo. And expandable collections, this is a collection which can grow. So there are many collections that we use in Pharo, actually in other languages that have this behavior to grow. So there is ordered collection, there is dictionary set. Actually, all the collections that are not fixed really apply to this work. When I write something like ordered collection new, what really happens? So here I create an object, this is an object, and this is C. And an instance of the class ordered collection essentially has two variables, one which contains an array and one which contains a size. So when I create an instance of that class here, the size is 0. But the array, the variable array, points to an array of size 10. And this is what happens now in your Pharo. So now when I want to add elements, okay, so that array has a size, the capacity of size 10. So when now I want to add some element to that things, such as 11 times repeat C at 42, then what happens? Then I have element that is added. So here I have the size now which become 1, then become 2, 3, and so on, until I reach here 10. So what happens with the 11 element I want to add in the collection? So here there is no space. So then there is a mechanism that called expansion of the collection. So this class, this object C has to be expanded. And the expansion is something like a bit complicated. So what happens in that case, after the 10th element has been added to the collection, then I have a new collection that is being created of the double size of that one. So here, the original size of the internal array is 10. Now I have an array of size 20 that is being created. And then I have all the elements that have been copied. So here 42 is being copied, and then here 42, until I reach to copy all the elements, and then here I have the 11th element. Then what happens is that this pointer here point now to the new array, which has a capacity of 10 or 20. And this is what happens. So with the previous array, then the array just gets discarded by the garbage collector. And that works well. I mean, this is what most programming languages do. We usually checked Ruby, Python, Scala, C#, and they all work exactly the same way for all the expandable collections we have. And that works well. We live, comfortably with that. But
yeah, just a question: the original size is always 10 or similar in
it's always 10.
Always 10.
When you write ordered collection, new is 10.
Yeah, but in Scala, Java, Ruby, etc.
This is always 10 except in the paper is written.
Okay.
Except in.
But usually it's 10. That's
usually it's 10. But I've seen cases where some language, I don't know, where it's Ruby, where it's 20 or 50. In the paper is written. And then, if instead of adding 11, what happens if I add, let's say, 30 millions? So here I have 30 millions that will repeat C at 42. And then I create another collection that way, of the collection new. So this takes, on my machine, this takes about 3 seconds. And what happens here is that there is 22 expansions. And these 22 expansions means that there is 164 megabytes that is copied between all the temporary arrays that is being created. So in the example I showed before, we started with an array collection. We added 11th element. There is 1 expansion. The capacity went from 10 to 20. When now I add 30 million, then we went to 10, 20, then 40, then 80, and up to the point where there is 30 million that can fit into the internal array. And now, this piece of code can be speed up quite significantly if I properly initialize the class here, the instance with 30 millions as an initial capacity. And then when I do that, then there is 0 expansion and 0 copied megabytes. So this is a bit this is to give the context of our work. And what the paper is about, there are essentially 3 points. The first one is to characterize the use of the expandable collections in Pharo. Then we measure the overhead associated with expandable collections, especially in terms of memory consumptions, and then we provide some optimization that are associated with expandable collections. So we won't go into the details of these things. We just give you a hint of what we have done. So to characterize the use of expandable collections in Pharo, then we took 17 applications for example in Pharo. Those are the applications. And here this is the column, this is the number of lines of code, and here this is the number of references of expandable collections. So in the paper we mentioned that the expandable collection which is used the most is order collection, and then is dictionary, I think, and then is set, something like that. So we pick these applications, and we use, for each application we provide two sets of benchmarks. The first one is running the unit test. Each of these applications comes from a fairly large test, large set of unit tests. And then we have written some benchmarks for, I think, five for this application. For this 5 application, we have written 3 benchmarks. So here this is the result of the execution we had. So here this is the execution of the unit test, and here this is the execution of the benchmarks. So I mean, the number at this point, right, is not that you read these numbers, but I will just give you like pinpoint like some of the value. So running the unit test of the 17 application plus running all the benchmarks, this created 8.6 million expandable collections. From these 8.6 million expandable collections, there are actually 23%, only 23% that actually use, that are filled with something. And you mean that there are 76% of the collection that are left empty at all. This happens essentially when you have, in the initialize method, the instantiation of some instant variables, with object collection U or dictionary U, and these variables, nobody uses them. And because of that, then we have, we have about like nearly 300 megabytes that have been copied by expansions, collection expansions. And because we have like over 1 million collection expansions, and yeah, so this is what we have, nearly 300 megabytes of byte that are unused. You mean that we have a capacity, we have the size which is much below the capacity, and we have a lot of memory that is wasted. So, so those are really impressive figures. So we try to optimize that. So we came with 3 optimizations. So we go one by one. So the first one is that we call lazy array creation. When we create object collection new, as I showed before, then I have an instance of that class here, and I have the array that points to an empty array. Now what we have with this optimization is simply to point that to nil. And then when I add an element, then this array gets created. This is what we have. And just this optimization has a very, very strong impact on the benchmarks. So we went, yeah. So here, like from these 8.6 million expandable collections, just with this optimization, then we went down to only 500,000 expansions, array creation, meaning that we have 77% less array that has been created. And this means that there is much less unused bytes, such as we have reduced the amount of unused memory by 72%, which is quite impressive. So that's for the first optimization. Then the second optimization is about recycling the array that had been discarded. So remember, like when I want to add the 11th element to that thing, so then I have the new array that's been created, everything has been copied. I have the 11th element here being added, and what happens to that guy? It just gets discarded by the garbage collector. Instead, what we are doing in the second optimization is that we keep that array and we put it in a pool. Actually, that array here, we recycle it by emptying first. We need to empty it because we want to get rid of, the references of some object and then prevent the garbage collector to clean the memory early. So we clean that object and we insert it in the global pool. So that pool actually can have a lot of array of different sizes. Most of the sizes contained in the pool are actually 10 because this is the default capacity. And when we create here an object collection, then first of all, we just go in the pool and pick one collection, one array that fits to that thing. And also we access the pool when we want to do an expansion. So yeah, create that. And then this has very, very small impact on the benchmark. So actually we were able just to reduce by 0.something% in the whole benchmark. So which has a very, very small effect. So in the paper, so we discussed different strategy to pick a collection, an array from the pool. But we didn't find any.
30% something, the second term to third term, which was 26 before one step.
Yeah, that half. Yeah, so here there is 13%.
Yeah. Before it was 26. The
Here the
number
other-
of arrays used or something.
Yeah, no, this is the number of non-empty collection. So here there is 13%. Maybe you can check that.
Yeah, well,
And yeah, it's true. It doesn't matter what 22%. I don't know what happens. Maybe I picked the wrong table here, but I don't know. And okay, so that was for the second strategy. The first one is to do lazy array creation. The second optimization is to recycle the arrays. And then the third one is to identify places in the code where I can actually initialize the object collection. So here we have a piece of code where I create an object collection here, and then I do I fill that collection with those elements here. And this piece of code here can be optimized, improved that way where the object collection here is first initialized with the right capacity. And so we have the profiler that said that return the list of methods that are actually creating a collection and filling the collections in the same method, because this is easy then to improve. So there are, like in all the benchmarks, there are about 170 methods, and we were able to refactor 50 of them. But we didn't see that much improvement. Oh, and here there is 23. So yeah, probably there was something wrong with the slide. And the thing is, we didn't notice any major improvement. Yeah, there is a bit, but not much. Okay, so that's this is what I wanted to show you. So the expandable collection are a really important piece of the runtime. I mean, most of the as soon as there is a loop being done, then there is a collection somewhere, and that's so it's really important, I think, to get it right and fast. So there are three optimizations that we show you: the lazy array initialization, the recycling arrays, and refactoring the applications. And by applying these three optimizations, we reduce the amount of memory being used by over 70%. Except this one here, I just said 67%. Yeah, so something like about the speed. So we just had a slight speed improvement, about 3%. But we were a bit disappointed by this 3%. We were expecting like something more. But it's really hard to understand what's going on with things. I mean, this is real benchmarks, real piece of code. There is use of primitives, also where time is being spent. So it's not really easy to understand how to improve the speed of that things. But for sure, we have reduced the memory consumption. So the lazy array creation, this is something I think we should adopt in Pharo, in Smalltalk. And this is something which is really easy to implement. And yeah, so this is something that I think we believe that should be part of the main runtime. Okay, so that's all. This is what I want to tell you. So thank you very much.
Yes, questions?
Yeah, so since it's so easy and we, in my company where we work, we build our own images, so I was thinking I'd just put that in like the nil fix, right?
Yep.
And then we could be, like we could increase the stuff we put on our servers, theoretically. Is there any danger at all that,
No, no, there is no danger at all. So the thing is, I discussed with some guys from Oracle, and the coming version of Java will include this optimization. So, but no, there is no danger at all.
do you have any idea why that wasn't done in the first place?
Oh my God, I think that nobody thought about that. That's the thing. And if you look at like so in Java, there's been a lot of work being done on the hash entries in the hash table. There's been really a lot of work being done on that. But besides, on the expandable collection in general, there hasn't been much work done on that. And in the paper, we usually went, that was painful, we went through Ruby, Python, C#, Scala, Java, and they all have the same problem, except actually one collection, I think, in C#. The equivalent of array list in C#, they have that thing. Actually, there is no need actually to have a need. You can just initialize the collection, the array with an empty array of size 0, and that has the same effect. But yeah, this is something which is really cheap, and I think we should adopt.
I have a remark about the third optimization, the modifying the code.
Yeah.
From my experience, it's a huge optimization if you have huge arrays to allocate before using your collection.
Yeah. So
if you have a huge arrays.
yeah. So the thing is, we indeed, like, there are some situations where obviously the improved situation. I mean, the example at the very beginning is exactly by that. But from what we have seen, we took some benchmarks. We didn't see any improvement. So this is really clearly against what one might expect. I mean, if you pre-allocate the thing, it should be faster. But in the average, apparently does not. This is what we have.
Yeah, after all, we have to ask ourselves what the size of the collection, like medium, the average size of the collection used in these applications. Basically, if you don't have large collections, like many elements, but you have just many collections, you won't see the benefit of allocation. But if you have many big collections, then you will see the benefit of allocation. So we maybe
Could be.
I don't know if you have counted also the number of elements in each of the collections.
Yeah. I mean, yeah, we have that. No, but the collection, not really. But what we have in the paper, we have distribution about the size. So you see that most of the collection actually are really small.
Yeah.
And this is something really frequent.
Yeah. So then that's why you didn't observe
That could be why we didn't observe that. A really large collection, actually, there were not that many. There were, but not that many. And also, like, the places where we can reallocate, there were actually not that many as well, where I can really say for sure, oh, here you can introduce things. So because we refactored the applications, but we didn't have much knowledge about them. So only when it was obvious that we changed. Then we run the test to make sure we didn't break anything. But
it might be interesting to run the test only on the applications with big collections. Only on those?
Could be.
So
could be. This is true that this is the point that about this. Yeah, because maybe we have pre-allocated only for small collections, for big collections, I don't know. But this is a bit hard to get. I mean, those data, we have a special profiler, a special set of the collection, this is not trivial to get. Okay guys, so thank you very much.